In progress. Okay, so this is homework 4, part B. We're going to be looking at this mixture here, right? We have our tube here, and we have the um, thing on top that eliminates pressure-driven flow, right? And so we have um, three things here. We have acetone, methanol, and then our air, which is just nitrogen. Uh, so we know a few things given in the problem, homework 4, part B, right? We know that the pressure that is going to be 99.4 kilopascals. We know our temperature is going to be 328 um, 5 Kelvin. And then we know our vapor pressures, or our vapor concentrations, right? So our Y1, our Y2, and our Y3. Right? Because 1 is corresponding to acetone, 2 methanol, 3 air, right? So Y1 is 0.319 millimeters squared per second. Y2 is 0.528 millimeters squared per second, then 0.153 millimeters squared per second, right? And we were able to get this last one because y1 plus y2 plus y3 has to equal 1, right? So we were given those and we just subtracted. Next, we were given the um, the diffusivity, or sorry, diffusion coefficients, and actually, this is the units for the diffusion coefficients, not the concentrations, right? So we have our diffusion coefficient from acetone to methanol, right? That is going to equal 8 point, that's going to be 8.48, right? Our D1 to 3 is going to be 13.72. And then our diffusion coefficient from 2 to 3, right? Methanol to air, that's going to be 19.91. Okay, so what we're trying to do is we're trying to find the evaporation coefficient, right? So what we need to do is use the equation that we used in homework 3, part D, I believe, which was Maxwell's Stefan equation, right? The Maxwell-Stefan equation, right? We know that is going to be, right, um, this equation here, right? We did this in homework 3, part D, and we got this equation, right? Where um, our y is multiplied by the opposite flux, right? So our yi is multiplied by yj. And so what we want to do here is we want to look at this for acetone, and methanol, right? So when we look at this for acetone and methanol, right, we can see, so um, D1 equals D Y1 DZ equals, and here we're breaking this up, right, because it's the sum. So we have our Y of acetone times our flux of methanol minus our Y of methanol times our flux of acetone over the concentration times our diffusion coefficient of acetone to methanol plus our Y of methanol times our our Y of acetone times our flux of air minus our Y of air times our flux of acetone over the concentration times the diffusion coefficient from 1 to 3, right? So those are our two things that will have substance. If we did, technically you could do a third one where it would be Y1 times N1, all that, because it's acetone to acetone, but that's just zero, so we don't have to do that for this equation, right? And then we can come down here to methanol, right? And so it's D2 equals dy2 dz equals, and now we break it down again, where it's y2 n1, right? y2 n1 minus y1 n2 over c d, and then this is going to be 1 2 because acetone to methanol doesn't matter if you're going from methanol to acetone or acetone to methanol. And then we will come here, add y2 times n3 minus y3 times n2 over c d 2 3, right? That's our third diffusion coefficient up here, right? And this concentration, right? We know that concentration equals our pressure over our RT, right? Our temperature times our molar constant, right? And so what we want to do with these equations is we want to be able to scale, right? So in the problem, we're given that this value here is 0.24 meters. Let me double check that. Yeah, so it's 0.24 meters, right? But we want to be able to scale this. And when we're scaling something, we're going to be using a scaling factor, right? So we'll use n here. And so this is our scaling factor. And this is typically between 0 to 1, right? And so we can write this equation as our n equals our z over our distance, right? And so we want to look at this as a differential, right? And so we can write it as dn equals dz over d delta, right? Sorry, not d delta, just delta, right? And we don't have a dn currently in our problem, right? So what do we have? We have our dz, right? So if we solve this, we get dz equals delta d times our scaling factor, right? And so now we can go in with this back into our equations that we solved down here. But before we do that, we can actually incorporate our y1 and our y2, right? So it'll be dy1 over dz equals dy1 over dn times our delta over dz. And then we can do the same thing for y2. So it's dy2 dz. And this is wrong. It's actually dy1 over dz, and then this is over dn, right? And then we can do the same thing here, dy2 over dz, delta over dn, right? And so we can plug these in over here, right? dy1 over dz, right? We have that over here. And so we can plug this in here to where it's dy1 over dz times our delta over our scaling factor, right? And then after that, it's actually, sorry, dz over dn, right? And then what we can do is right? We just bring this whole initial problem down, but now we're multiplying it by what we just multiply the other side by, which is dz over our scaling factor, or dz over the change in our scaling factor, right? And so when we look at this, right, these dz cancel, and we get our expression to have dy1 over d times our scaling factor. And this is good because, right, it will be about 1, right? Because we are going from 0 to 1, so we can assume that it's about 1. And then this, right, well, that's just our delta, right? So now we're just multiplying our original thing by the length of our tube. And so you get the equation dy1 over our scaling factor equals the delta times our original term up here, right? I'm going to copy it here because it's a little easier. Right. So now we can put this in. Sorry, that's bad. Right. And so this equation is a lot better because it allows us, it's able to be scaled, right? And we can do the same thing down here with this. Just plug in or multiply by the same thing we did up here. And so then we'll get dy2 over dn equals our delta times this value here. Right. And we're looking at the same thing as the acetone. And then once we have this, what we're able to do is multiply this out, right? So we can simplify a little bit. So dy1 over dn equals y1 times our delta n2 over cd12 minus y2 delta n1 over cd12 plus y1 dn3 over cd13 minus y3 delta n1 cd13. Now when we look at this, right, our flux for our N3 here is just 0 because, right, we have no pressure driven flow up here. And so this can just go to 0. And so we can simplify our equation down even further to y1 delta n2 cd12 minus y2 n1 cd12 minus y3 n1 cd13. And then this can be solved to get a value for N2, which will be how we are able to make an initial guess for when we were plugging this into Excel, which I'll do later in this video. But we are then able to make a guess based on the Maxwell equation, right? And so we get N2 to equal, we get that to equal delta times, or sorry, cd12 over delta with some math, and then we can plug in what our C is, right? So we'll get that equal to pd12 over RT delta, right? And so when we do this, we can look at just kind of the magnitudes of the individual elements to get our guess here, right? So pressure, right? That is 99.4 kPa. So that'll be about 100 times 10 to the -3 pascals, right? Our D12, that's our 8.48 millimeters. These are all millimeters squared per second. So we'll get about 10 times 10 to the -5 meters squared per second, right? Then we have our 8.314 for our R, that's about 10. Our temperature, which is 328, which is about 300. And then our delta, which is about 0.2, right? And so when we do this, when we solve that out, we get N2 to equal 1 over about 600. And we can assume that N2 equals N1 because they're about the same. So with that initial guess, right, I'll move on to doing this in Excel, and we'll just be solving this this initial problem up here with our initial guess using that we found using Maxwell's equation. Right. So I will switch over to Excel. Okay, so this is the second part of homework 4 part B, right? So we just did all of oh, okay, all of this, and I'm going to be using these equations in this part. So what I have in here right now, right? We have our y1, our y2, our y3, right? We had those defined. We had our d1, or d12, d13, and d23, right? Those are diffusion coefficients. Those were defined. We have our pressure, temperature, and molar coefficient or constant. And then we have our step, right? So what do we need to put in here? We need to put in our concentration, right? Right. So that's going to be our pressure. Right. Hold on. It's going to be our pressure divided by our temperature times our R, right? And so that's our concentration value, pressure over RT. And then we have our DZ value, which is just however many, or our scaling factor, right? So we have our D divided by 1,000, right? The other thing we need to add here is our initial guesses, right? So N1 and N2, right? We said both of these were 1 over 600, right? That was what we found using Maxwell's equation, right? And so with this, we can then start our problem here, right? So we will be looking at this for 1,000 steps. So what we want to do here is what we want to do here is so we are sorry, we are going to fill this down columns to 1,000. Or not. Make columns 1,000. Okay, and so that goes all the way down. And here is going to be our z multiplied by our step, right? And we can send that all the way down, right? Um, yeah, yeah, okay. So now that we have that, we can put in our other values, right? We have our y1, y2, y3, right? And so initially that is just going to be this, right? Our initial values. And then next, what we're going to look at, right, is we're going to look at our equation, um, and it's going to be dy1 over our dn, right? And so what does that equal, right? We know that it's going to be negative. Um, then it's going to be our y1 times our n2, right? Minus our y2 um, times our n1, and then divided by our concentration times our d12, and then plus, nope, uh, plus, um, and it's going to be negative y3 times n1 divided by our concentration again, and then this time multiplied by d13. Yep. Um, let's see. Oh, sorry, this should have a negative sign. Right? So that is, right, that's our dy1 over dn, right? That is just the equation. Let's see. That is just this equation that we have from the first part of this video. And then we can look at the second part, or the second equation, which was dy2 over dn, right? And so what does that equal? Well, that equals um, our y2 times our n1 minus our y1 times our n2 divided by C, right, our concentration times our diffusion coefficient, right, and then plus our negative y3 times n2 divided by our concentration times our d23, right? And so we get this value here, and um, from here we're able to then move on to this second row here, right? And so what this second row is it's just um, it equals our y1 times our step value times the change in y1 here, right, that we just found. Ooh. Um, G3, what? Right. And so we then do the same thing here, right? So that equals Y2 times our step um, times our dy2 this time, right? And then for the y3, it is just 1 minus these two values. Oop, um, right. And so these two will just so from that these will go down, um right, and we're referencing these cells over, right? So it just changed by 1, so we can then send that all the way down. Okay, so we have a problem. um that problem is this is not times F4. This is times our dz value, right? And then this is also times our dz value. And then we can take this value, send it all the way down, and um, so I wiped all that. I had this incorrect again. I had it as G3 times. It is actually G3 plus, and that's the same for H3 here. So, um, so what we can do is we can bring this down, right? And then bring these all the way down, right? And we have no crazy numbers here, um, right? But what are we trying to do? What we want is for these two values to go to 0, and this value to go to 1 because um, at the top of um, our tube, right, it is just pure air, right? So how do we do that? Right, what we want to do is over here we're going to put um, equals G 1003, then equals H 1003, right? So this is our Y1 and our Y2 at 1,000. So what we want to do is a sum squared. So if we do equals sum squared of these two, right? So what we are going to do is um, we're going to take this and um, actually I just noticed this. I have this um, referencing the wrong cell. Um, it should be DZ, right? We should be referencing this cell here, and then this can go all the way down, which then um, will then shift, right? Um, I actually have an error going on here somewhere, so I'm gonna clear out these values here. And I believe it's here, right? So if I'm looking at this, let me pause this real quick. So I was actually missing some parentheses here. So we can redo this section here, right? That is going to be our y1 plus our change in y times our dz, right? This is going to equal our y2 plus our dy2 times our change in z. And then this is going to be 1 minus y2, oop, 1 minus y2 minus y1. And these can be brought down. And when we do this, we can then bring that all the way down. And we can see that, right, we want to get these y1 and y2 values. That's all the way at the bottom, like I did earlier, and then had to redo, right? So we want to minimize that, right? We want that to go to 0. So we want our sum squared to go to 0. So if we go to solver, right, and we're trying to get that to minimize by changing. Now, what are we changing, right? What did we guess, right? So in the initial problem, we found 1 over 600 as our guess for n1 and n2. So we are changing these two values, and we're going to let solver solve that. It'll take a second because we have a lot of values here. And when we do that, we get point or 2.65 10 to the negative 8, which is nearly 0, right? Both of these values are very close to 0, right? And so we then know that our N1 and our N2 are these 0.00175 and 0.00308, right? And so what was our initial guess, right? That was our 1 over 600, right? So if we're looking at this, like our N1 is almost perfect, right? And we're about half of our N2. That makes sense. But that shows that our Maxwell's equations gave us a relatively decent guess for the values of N1 and N2, right? And so that's our answer to this problem.